Hi folks, Erich Osterberg here again with you, Associate Professor in Earth Sciences at Dartmouth College. So in the last episode, we were talking about finding evidence, so scientific data, to investigate these anecdotal reports that the summer of 1816 was unusually cold, that it was so-called a year without a summer. So in this episode, we moved into my office here and we're going to do exactly that. We're going to first look for evidence in the tree ring record to see if we can figure out just how cold the summer of 1816 actually was. Was it really an unusually cold year, as these anecdotal reports suggest? And then we're going to go to the ice core records to see if we can find any evidence of a climate disruption that may explain anything unusual we see in the temperature record. But first things first, let's see just how unusually cold the summer of 1816 actually was. Let's see if we can find evidence in the data for the actual temperatures in 1816. So if we're going to be looking at scientific data, we're going to need to take our notebooks out because we're going to be writing the data down, we're going to be plotting it up in a chart, we're going to be taking some notes, and then together we're going to see if we can figure out this climate puzzle of the summer of 1816. So pull out your notebooks, and let's start off by in the top of the left-hand side of the page. We're going to list our goals for this exercise. So our first goal is going to be, can we see any evidence for unusually cold conditions in the summer of 1816? And then the second goal will be, can we see any evidence for a climate disruption that might explain that? And then below these two goals on the left-hand side of the page again, we're going to create a data table. So using a ruler, let's create a table that has 4 columns. And then all the way on the left in the first column, we're going to create the year of each observation. So if we're interested in the summer of 1816, we're going to need some context if we're going to figure out just how weird 1816 was or not. Right? So let's start off before 1816. Let's start off in the year 1804. And let's continue on past 1816 all the way down to the year 1820. That way we get to see what happened before this unusual summer and then what happened after. And so let's write down each year from 1804 to 1820 in that first column on the left. And then in the second data column, we're going to be looking at the tree ring data. So let's put a header at the top of the second column called Tree Ring Growth Index. And then we're going to hear a little bit here from Layla about how we're going to interpret the tree ring data.
Hey everyone, welcome to Layla's Zoom Minute. Today I'll be talking to you guys about the Tree Ring Growth Index and how it can be used to show different climate markers. So the Tree Ring Growth Index compares the growth of a tree each year to an average index. Wide rings indicate good growing years, which typically show good warm years and lots of rain and indicate higher index numbers. Thin rings represent poor growing years, which have cool temperatures and little to no rain, and that corresponds with lower index numbers. As you can see here, using this sample of a tree ring, good growing years and poor growing years can be marked in a graph. Wider rings, again, show good growing years, which have warmer temperatures and more rain. Thin rings, again, represent poor growing years with cooler temperatures and little to no rain. So to summarize, wide rings, good growing years, higher index numbers. Thin rings, bad growing years, lower index numbers. That's all you really need to know. Bye.
So the tree ring data that we have is about 10 years in between 1804 and 1820. So let's jot those down now. In 1804, we have a growth index of negative 0.34. And then there's about 10 total data points that we can fill in here. So take a moment and write these data down in your notebook. Feel free to pause the video so that everybody is on the same page, and then we'll continue and plot it up. So now that we have some data, we're going to plot it up on the right-hand side of the page. So using a ruler again, let's create a couple of axes, a vertical y-axis and a horizontal x-axis. And what we're going to do is plot the tree ring data down below the horizontal axis, because as you can see, all the tree ring data that we have are negative values. And then eventually what we're going to do is actually plot the ice core data in the same chart in the positive side of the y-axis. So let's start off and create our axes. And if you look at the data, you can see that we range from close to 0 all the way down to about -3. So let's create some axes that go from 0, and we'll do a spacing of every 0.5. So you can write 0, -0.5, -1, and so on that y-axis. And then the x-axis, of course, is going to be the years, our yearly observations. So it'll start in 1804 on the left and go all the way up to 1820 on the right. So take a moment to create these axes and label them appropriately. And again, pause the video when you need to. So now that we have our axes, we can actually plot the tree ring data. So going down with each year, just plot the data points out and then connect them with a straight line. You can use your ruler to make it nice and neat. And we can actually see how 1816 compared to the years before and after in terms of temperature as recorded by the tree ring growth index. And so then what we want to do once we have it all plotted is write down 2 things that I notice and then 1 thing that I wonder. So looking at these data, 2 things that I notice. First of all, it looks like 1816 really was a really unusually cold summer. But what's interesting is that it's not just 1816, right? We actually had cold summers for several years before 1816, going all the way back to 1809. So the 2 things I noticed, the first is yes, 1816 was a cold summer. But 2, it's not the only summer that was cold during that time period. We had several years that were colder than normal at around this time, and the first one was in 1809. So something I wonder is, could it be the same climate disruption that is causing all of these cold summers? Or do we actually have 2 or more different climate disruptions that could be causing this? So in order to answer those questions, we need to actually go to the ice core record and see if we can actually see evidence of these climate disruptions that might be causing these cold summers. So let's talk about what an ice core is and how we actually go and collect them. So an ice core is just a long tube of ice that we collect from a glacier, so either Greenland or Antarctica or the top of a really high mountain. Basically anywhere that we have glaciers today in the world is a place where you could potentially collect an ice core. So if you think about a glacier, it snows every year, usually all year long. And the snow gets preserved every year because it doesn't all melt in the summer. So if you think about it, in a glacier, each year's snow is getting covered by the next year's snow, and so on, and so on, and so on. So that the glacier is actually preserving the snow going back for hundreds of years, or even tens of thousands of years. And so if you go to the glacier and actually drill an ice core down into the glacier, what you're actually doing is drilling back through time. The deeper you drill down, the further back in time you go. The key is that it's not just snow that gets preserved in the glacier every year. Anything else that's in the atmosphere will also land down on the glacier and get trapped in with the snow. So that means stuff like dust, or salt from the ocean, or pollution, or CO2, or volcanic eruptions. Anything that's up there in the atmosphere will eventually filter on down to the surface of the glacier and get trapped with the rest of the snow. And just like we were talking about with the tree rings, each one of these things can give us an indication of what the climate was like in the past. So for example, if it was windier in the past, we would expect to see more dust blown up into the atmosphere, and that means more dust landing down on the glacier and being preserved there, where we can collect it with an ice core. So for this project, we're interested in looking for climate disruptions from here in New England and in Western Europe back in the early 1800s. So a really good place to go for an ice core would be Greenland, because that's right smack in the middle between New England and Western Europe. So how do we actually go to a place like Greenland and collect an ice core? Well, first we actually have to get there. So sometimes it means we're taking large military airplanes. Sometimes we're on much smaller ski planes, so planes that actually have skis instead of wheels. Sometimes we're on helicopters. Sometimes we're on snowmobiles. If we're in the mountains, like in Alaska, sometimes that means we're actually mountaineering or we're on skis. What's kind of neat about ice core expeditions is that every single expedition is a little bit different. So it's never going to be quite like the one was before. And you never really know what to expect because you're in the polar regions, right? The weather can be really crazy and very unpredictable. All ice cores are collected with some kind of special drill that's specifically designed to collect ice cores. But what's really neat is that we actually have a whole suite of different drills that we can use depending on where we are and how deep we want to drill. So sometimes we want to use just a really lightweight, simple drill that just I could operate on my own. And maybe that drill can only go back 50 or 100 feet down into the glacier, and maybe that only gets us back 50 years in time. But that might be exactly what we're looking for. Other times we might want to go back tens of thousands of years. And some drills that we have are really huge industrial drills. They take like 10 or more people to actually operate them. And those drills can actually go over 2 miles down into the glacier, all the way to the base of Antarctica or the base of the Greenland ice sheet. And those ice cores can go back tens of thousands of years, sometimes hundreds of thousands of years in time. So every expedition is different depending on exactly what we're trying to do. So usually when I go on one of these expeditions to collect an ice core, I'm gone for at least 3 weeks, sometimes as long as 3 months. And some of these projects can go on for several years. So there may be a team of 10 or 15 or more people there for 3 months, and then they go back the next year because we can usually only work during the summers when the weather is good enough to actually be in these really extreme places. So when we're on these expeditions, we're always camping. So that means that we are sleeping, we are eating, we are working every single day for that whole time on the glacier. And so if you enjoy snow camping, it can be a lot of fun. If you don't, it may not be for you. So we have lots of different ice drills, but they all basically do the same thing. Basically, they go down into the glacier and they're drilling down and they're pulling up a cylinder of ice, usually about the diameter of a coffee can. And it'll probably pull up between 5 and 10 feet of ice every time you put it down into the glacier. So I want you to imagine this drill going down into the glacier, just going back down into the same hole over and over and over again. And every time it goes down, you drill the next 5 or 10 feet of ice core, you pull it out, you take the ice core out of the tube, and you put it into a special box to ship it home frozen, and then you put the drill back down into the hole to collect the next 5 or 10 feet of ice core. So you can imagine if you're trying to go back over 2 miles of ice, it can take a while. So let's head down to my freezer and actually start processing an ice core from Greenland that we know is right around the time that we're interested in, right in those early 1800s, and see if we can find any evidence of a climate disruption that would explain these really cold summers. All right, so we're down here at my ice core freezer. As you can see, it's pretty cold. It's saying 0 degrees Fahrenheit right now. And actually, what we have here is a refrigerator where we keep sediment core samples from lakes. And so that's at 38 degrees. And then over there, we have the actual freezer. And it's helpful to have the freezer going off the fridge because that way the air going into the freezer is already pretty cold. But it's 0 degrees Fahrenheit in there, so we're gonna have to suit up in order to go in there and work comfortably and safely. All right, I'm all suited up in my clean suit, and we're ready to head into the freezer. So let's go. In this freezer, we got ice cores from all over the world. GT stands for Greenland. Greenland. SP stands for the South Pole of Antarctica. We've got some cores over here from Alaska. So what we're going to do is focus on Greenland ice cores. What we need to do is cut the ice core into pieces and then sample them and melt them really cleanly into little bottles. So here's what an ice core looks like. Well, actually this is about half of an ice core. It's been cut in half, but you can imagine it having a mirror image on the other side. And so this core is from Greenland, and you can see in this core we can actually see some of this banding representing different layers in the ice core, or different years in the ice core. What this represents actually is the summer when there's a little bit of melt on the surface of the glacier, and that meltwater refreezes as a clear layer that looks like this. And the rest of the ice core is white because that's the snow that's been pressed down under the weight of the overlying snow year after year after year. So the idea is we're going to cut this into little pieces and then shave off the outside of the core using a special lathe. And that way we're only sampling from the very middle part of the ice core, the part that hasn't seen the light of day since it first deposited on the glacier hundreds of years ago. Because we know that these bags and the saw and me, we contaminate the ice core, and we don't want to see any of that contamination in our samples. So we have to scrape away the contaminated snow on the outside of the ice core and just analyze the really clean snow that's still stuck in the middle of this core. Alright, so now we have all of our ice core samples. We've scraped off the outside that might be contaminated. We put those samples into the clean jars, and those clean jars have now been sitting under clean air and allowing the ice samples to melt. So now in each one of those jars is water that represents that section of ice core that we sampled in the freezer. So now we just have to put those in the vials that we can actually load in the instrument and then measure the chemistry and see what's going on, see if we can see any evidence of a climate disruption. Alright, so now we've got all of our samples ready to load into the instrument. This is an ion chromatograph instrument. This will measure the chemistry of each one of these water samples, looking for the major ions. So this will be things like the salt and the dust, the stuff that represents 99% of the stuff that's in the ice core. So once we've loaded this all up, we can launch the program, and it'll spend a couple hours and actually measure the chemistry of each one of these ice core samples. So overall, we measure pretty much everything on the periodic table. That instrument will just cover a few of them, the big ones like sodium and magnesium and chloride and sulfur. But we have other instruments that basically analyze everything on the periodic table here. So if there's a climate disruption in the ice core at that time, we're going to find it. All right, here we have the actual data. We've got it back from the instrument. And there's a lot of data here. We've got sodium, we've got ammonium, potassium, magnesium, calcium. But when I'm looking at these data, the one that looks the most interesting to me is sulfate. And so why don't we start there? We're going to plot up the sulfate data and see what we can see, and then think about what kind of climate disruption that might represent. So what we're going to do is go back to your notebooks, and we're going to record the sulfate data from this Greenland ice core in the second column. So at the top of that second column, let's label it as Greenland Ice Core Sulfate, and you can see the 10 different values of sulfate in parts per billion that we were able to measure on our instrument. So take a moment and pause the video so you can write down these values, and then we're going to plot them up on the other side of the paper. Okay, so now you've had a chance to record the data. Let's go to the other side of your notebook page where we've already plotted the tree ring data. And on the top of the y-axis, we're going to plot this ice core sulfate data from Greenland. So starting with our top value, we're going to plot that up. And then just like we did with the tree ring data, we're going to connect the dots with a ruler and see what we can actually see in terms of changes in sulfate with time. So take a moment and do that, and pause the video if you need to, and then we'll talk about what we see. So if we look at the sulfate data, it looks like there actually is a relationship between these cool summers in 1816 going all the way back to 1809 and two spikes in the sulfate data from Greenland. And so sulfur, or sulfate in this case, comes usually from volcanic eruptions. And so when a volcano erupts, it spews lots of sulfur gas into the atmosphere. And some of that sulfur gas turns into sulfate. So it does look like we have evidence for two volcanic eruptions, one in 1809 and one around 1816, that may have actually caused these unusually cool summers during those years that we can see in the tree ring record. And there are anecdotal reports that there was a huge volcanic eruption all the way down in Indonesia called the Tambora eruption in 1815. But in order to cause a climate disruption like this, it would have to be a really huge eruption. And we know that there are volcanic eruptions going on all the time all around the world. I mean, Greenland is right next to Iceland, and Iceland is basically just a whole group of volcanoes with eruptions happening all the time. So how do we tell the difference between an eruption that may be kind of small but really close, like from Iceland, versus a really huge eruption that may have actually caused a climate disruption? So for that, we actually have to go to Antarctica. Because if it was a huge eruption, we should see it all around the world, including down in ice cores from Antarctica. So luckily, I've got an ice core from the South Pole, and we can melt and analyze that and see if we see the same signature in the sulfate record there. So let's go do it. So to analyze the ice core from the South Pole, instead of cutting it up into little pieces, we're actually going to melt it here on a specialized melting system. This actually separates the water from the inside of the core, which is that pristine water, from the outside of the core, which might be dirty. Instead of slicing it off by hand like we did with Greenland, this actually does it automatically. And then the water melts and can actually get passed through these tubes and pumped all the way down into these individual bottles. This way, instead of actually getting one sample for every 5 or 10 centimeters of ice core, we can get one sample every centimeter of the core. And that's really important down at the South Pole because it doesn't snow very much down there. We only get about 5 inches of snow every year down there, whereas up in Greenland it's more like 3 feet every year. So after that, once we have the sample in these bottles, it's the same process as before. We just load them up in the instrument, analyze them, and we see what the chemistry data shows us. All right, so now let's add the South Pole sulfate data to our table on the left-hand side of the page in that third column. You can title this column Antarctic Ice Core Sulfate, and we'll record 10 data points or so. It may not be for all the same years that we have the Greenland sulfate data for, but let's plot these up and see what story we can tell. So now on the right-hand side of the page, we're going to plot the South Pole data right up there with the Greenland data. Now, you're going to want to use a different color this time so you can tell the difference between the Greenland data and the sulfate data from Antarctica. So make sure that you include a key at the top of your chart showing which one is which. So take a moment to plot the data up. Feel free to pause the video to make sure you have enough time to do that. And then we're going to look at the data and really think about what is the story that we see here. So when you plot up the data from the South Pole, it looks something like this. Really interesting. So I want to take a moment now to actually spend some time with your classmates and your teacher, look at the data and see what story you think this data is telling us about what's happening between volcanic eruptions as recorded by the ice cores and temperature as recorded by the tree rings. So take a moment once again to record 2 things you notice and 1 thing you wonder, and feel free to pause the video here to spend the time that you need to do that. So if we think about those 2 questions that we started this episode with, first of all, it does look like we can see clear evidence in the ice core record for an unusually cool summer, not just in 1816, but going all the way back to 1809. And then in terms of climate disruptions, it looks like we can see evidence of 2 volcanic eruptions that are seen in both ice cores in Greenland and all the way down in Antarctica at the South Pole. So in episode 3, we're going to think about what does this mean in terms of modern climate change caused by humans, and how we might actually be able to fight climate change going into the future. So tune in for that. GoPro, stop recording. 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 GoPro, stop recording.